Hello everyone, I welcome you all for this lecture series on system of linear equations. In this series, we will discuss various topics related to a system of linear equations, and we will focus mainly on Gauss elimination method and Gauss-Jordan method. In today's lecture, I will focus mainly on the applications of system of equations, basic definitions, elementary operations, and we will discuss in detail system of two equations in two variables and geometrical interpretation of system of three equations in three variables. System of equations, especially linear equations, play a very important role in subject of linear algebra, and we will see that various numerical problems or practical problems reduce to finding the solution of a system of equations. I will discuss some applications of linear equations, mainly traffic flow, electrical networks, and there are many more. Consider a very basic problem. A chemist wants to make 15 liters of a 23% acid solution by mixing two different solutions, one with 12% acid solution and other one with 27% acid solution. Now the problem is how many liters of each solution should the chemist use so that we can have a final product with 23% concentration and total quantity is 15 liters. So let X be liters of 12% solution and Y be liters of 27% solution. So if we are taking X liters of first solution, Y liters of second solution, and then we are mixing. So the total quantity of the solution will be X plus Y, and we want total quantity as 15 liters. So the first equation is X plus Y equal to 15. Now consider the concentration part. We want the concentration of final solution as 23%. Now 23% means if I am taking 100 liters of the solution, then 23 liters is the amount of the acid in that solution. So if I am taking X liters of 12% solution, it means what is the total amount of acid in this one? It will be 0.12 into X. Similarly, for the second solution, if I have Y liters of the solution with 27% concentration, then the total quantity of the acid will be 0.27 into Y. Now in the final solution, I want 23% concentration and the total quantity is 15 liters. So the total amount of the acid will be 0.23 into 50. So this way we get the second equation, 0.12x plus 0.27y. This is equal to 0.23 times 15. We can multiply by 100 on both sides. So finally we have second equation, 12x plus 27y equal to 345. So finally this chemist problem reduces to a system of two equations in two variables. Now one more example. It took Raman 5 hours to motor a boat 30 kilometers upstream. His return trip the next day took 4 hours. We have to find out the speed of the boat in still water and the speed of the current. So let us assume X be the speed of the boat in still water and Y be the speed of the current. Now one very simple observation, that when we move upstream against the flow of the stream, in that case the velocity or the speed of the boat will reduce, and when we move along the stream or down the stream, the speed will add up. So we have the following mathematical form. I am writing the distance, rate I am writing the speed, final, and the time. For the upstream and downstream motion, distance will be same, so I am writing 30 kilometers. Now for the upstream motion, the speed of the boat will be speed of the boat in still water minus speed of the current. So it is now X minus Y. Time is 5 hours. For the downstream motion, the speed of the boat and the speed of the current both will add up, and the speed will be x plus y. Time will be 4 hours. We know the formula, speed into time, this is equal to distance. So we have two equations. 5 times x minus y equal to 30, which implies that x minus y equal to 6. Second one implies that 4 times x plus y, this is equal to 30, which implies that x plus y, this is equal to 15 by 2. So finally, we have again two equations in two unknowns. We can find out x and y. Now consider this problem. It is very much related to all of us. Photosynthesis. We know that photosynthesis is the process in which oxygen is produced, right? So it is a chemical reaction that occurs in the leaves of the plants that converts carbon dioxide and water to carbohydrates with the release of oxygen. Right, we have all these formulas. Carbon dioxide is CO2, water H2O, carbohydrates and oxygen O2. During this chemical reaction, A molecules of carbon dioxide, they react with B molecules of water and they produce C molecules of oxygen and D molecules of carbohydrates, where these A, B, C and D all are positive whole numbers. Then using the law of conservation of mass, the total mass of all the substances present before and after a chemical reaction remains the same. So using this concept, I can say that the carbon atoms before the reaction, we have A, and after the reaction corresponding to carbohydrates, we have 6D. So corresponding to carbon, we get the first equation A equal to 6D. Similarly, for oxygen, we have 2 times A, and for water we have B. So 2A plus B on the left hand side, and on the right hand side we get 2C corresponding to oxygen, and for carbohydrates we get 6D. So on the right hand side we have 2C plus 6D. Similarly, we can write down for hydrogen atoms and we get 2B equal to 12D. So we have a system of 4 variables in form of 3 equations. So this is a linear system of equations. So see how photosynthesis is a basic chemical reaction. We can have some relation with mass, that is system of linear equations. So finally I am coming to the definition of a linear equation. A linear equation in unknowns x1, x2 and xn is an equation that can be put in the standard form given by equation number 1, a1x1 plus a2x2 plus an xn, this is equal to b, where this a1, a2, an and b all are constants. These ai's, they are called coefficients of these variables. So we say ak is the coefficient of variable xk, b is the constant term. Consider the example given below. X equal to 1, x plus y equal to 5, 2x1 plus 3x2 minus x3 plus 2x4 equal to 12. Right, so these are different equations, linear equations with different number of variables. Solution of a linear equation. Given linear equation in the form 1, a solution of this equation is defined as a list of values for the unknowns or a vector u in Rn defined as x1 equal to u1, x2 equal to u2 and xn equal to un, or you can rewrite this in the form of just a vector u which is equal to u1 comma u2 up to un, such that if we assign xi's these values ui's, then the equation is satisfied, that is a1 u1 plus a2 u2 and so on an un, this is equal to b, and we say that u is a solution of this equation and it satisfies a given equation 1. Let us consider this example, 2x plus y plus z equal to 3. This is one equation and the number of variables is 3. So here we can have lot of solutions. So consider the first option. X is 1, y is 2, z is -1. Substitute these values in your equation. We see that on the left hand side we again get the value as 3. So this is a solution of this linear equation. Now come to the next one. X is 1, y is -1 and z is 1. If we put all these values in this equation, then we have just 2 on the left hand side, but right hand side is 3 and 2 is not equal to 3. So we say that 1 -1 and z equal to 1. This is not a solution of this linear equation. You can try the next one. X as -1, y equal to 3 and z equal to 2. This is also a solution of this linear equation. System of equations. A system of equations is a list of equations with the same unknowns. If all the equations are linear, then it is called a linear system of equations. So here system 2 is a system of linear equations with number of equations as m and the number of variables is n. So the first equation is a11x1 plus a12x2 and so on, a1n xn, this is equal to b1. Similarly we have second and we have up to m equations where all these aij's and bi's, they are all constants. Aij is the coefficient of variable xj in the ith equation and this bi is called the constant or the right hand side of the ith equation. This given system of equations, which we represented by 2, it can be rewritten in the form of matrix. So this is the matrix representation of a linear system of equations. We represent as ax equal to b, where this a is the coefficient matrix and this is aij m cross n matrix. Capital X is the variable vector x1, x2 up to xn. Capital B is the right hand side vector. We denote as b1, b2 up to bm. Here if m is equal to n, then this system is called a square system. Number of the variables and the number of the equations is same. Now if bi, that is the right hand side of these equations, as we discussed in system 2 also, if this bi is 0 for all values of i's, that is the right hand side of all the equations, they are 0, then this is called homogeneous system of equations. If this capital B is non-zero, then it is called a non-homogeneous system of equations. Consider this example. First one is homogeneous system of equations with 3 equations in 3 variables x, y and z. The first equation is x plus y plus 2z equal to 0, minus x plus 2y minus 3z equal to 0, and the last one is 2x plus y equal to 0. So you see here the right hand side of each equation is 0, so this is homogeneous. The next system is non-homogeneous. It is almost similar to the homogeneous one on the left hand side, but the only difference is right hand side of these equations, they are non-zero, like 5, 11 and 13. So the second system is non-homogeneous system of linear equations. Now we know very well what is an equation or a system of equations. So next one is, what do you mean by solution of a system of equations? So a solution or a particular solution of a system 2, that is system of linear equations, is a list of values for the unknowns that is a solution of each of the equations in the given system, that it satisfies each and every equation given in the system. Next is solution set. It is the collection of all the solutions of the system of equations. Consider this example. 3 equations in 3 variables x plus 2y minus z equal to 2, 2x minus 3y plus 6z equal to 5, minus x plus 4y plus 2z equal to 5. So clearly you can check if you put x equal to 1, y equal to 1, z equal to 1. Then this is a solution of this system. Consider this one more system of equations. X1 plus x2 plus 4x3 plus 3x4 equal to 5. Second equation is 2x1 plus 3x2 plus x3 minus 2x4 equal to 1. And the last is x1 plus 2x2 minus 5x3 plus 4x4 equal to 3. So this is a system of 3 equations in 4 unknowns. So let us check u, which is as minus 8, 6, 1, 1. Now the question is it a solution of this system of equations? So just substitute x1 equal to minus 8, x2 equal to 6, x3 equal to 1, and x4 equal to 1. And we see that all these 3 equations are satisfied by these variables, that is vector u. So this is a solution of this system. Now come to the second example here. X plus y plus z equal to 1. And the next one is 2x plus 2y plus 2z equal to 3. So this is a system of 2 equations in 3 variables. Now what can we say about its solution, whether this system has a solution or not? Now here there is no solution for this particular problem or system of equations, because if you see the second equation, 2x plus 2y plus 2z equal to 3, you can divide here by 2, and finally this equation reduces to x plus y plus z equal to 3 by 2. And if you see the first equation, we want x, y and z such that x plus y plus z equal to 1. But second equation implies that x plus y plus z, it should be equal to 3 by 2, which is not possible. So this is a system which has no solution. So depending upon these 2 questions, we can say that for a given system of equations, we have 2 options. Either the system has a solution or it has no solution. So these are the next 2 definitions. Consistent system. A system of equation is said to be consistent if it has 1 or more solutions. For example, x plus y equal to 1. Then this is a system of just one equation in 2 variables, and it has infinite number of solutions in 2 dimension. I'm just restricting myself to 2 dimension for this equation x plus y equal to 1. Because every point on this line, if you draw it geometrically, then every point on the line x plus y equal to 1 is a solution of this equation. You can take 1, 0, 0, 1. You can take half value for x and half for y. So we have infinitely many solutions. Now consider the second system, x plus y equal to 1, x minus y equal to 1. So we have 2 equations in 2 variables x and y. If you draw these 2 equations, these lines in plane R2, then they will intersect at a unique point, and that point is 1, 0. So we say that this system has a unique solution, and that solution is 1, 0. Next is inconsistent system. A system of equations is said to be inconsistent if it has no solution. Consider this example, x plus y equal to 1 and 2x plus 2y equal to 1. This is a system of 2 equations in 2 variables, and we see that this system has no solution. If we restrict our choice up to 2 dimension, that is R2, we can talk about 3 dimension also, but for simplicity I'm just restricting up to R2, that is 2 dimensional space. So first equation implies that x and y are such that their sum is 1. But if we divide equation 2 by 2, then it says that x plus y equal to half, which is not possible. So this system of equation is inconsistent. So for a given system of equations, we have following options. Either system is inconsistent, it means it has no solution, or the system is consistent with 2 options with a unique solution or infinite number of solutions. the system of equations which we defined in 2, this system can be represented by matrices. So corresponding to that system 2, we have two associated matrices. First one is matrix A and the second one is matrix M. This A is called the coefficient matrix, and if you see this matrix, see the first row, A11, A12 up to A1n. These are the coefficients of variables x1, x2, xn in the first equation. Second row corresponds to the coefficients of these variables in second equation, and similarly we have the last row, that is the mth row of this matrix. So this matrix A is m cross n matrix, corresponding to the coefficients of the variables xi's in the linear equations. Now matrix M, this is a matrix with m rows and n plus 1 columns. First m columns of this augmented matrix are same as the coefficient matrix A, and the n plus 1th column is the one corresponding to the right hand side constant, that is b1, b2, bm, corresponding to the system of equations. So this matrix M, that is the augmented matrix, completely describe the system of equations. So in the last we can say that capital M, that is the augmented matrix, it is AB coefficient matrix and the right hand side vector of the system of linear equations. A linear equation is said to be degenerate if all the coefficients are 0. For example, 0 times x1 plus 0 times x2 and so on, 0 times xn equal to b. So we want to find out these values of variables x1, x2, xn such that this equation is satisfied. Now the solution of this degenerate equation depends on what is b, that is the right hand side of this linear equation. So we have following result for this degenerate linear equation. If b is not equal to 0, then the equation has no solution, and if b is 0, then every vector u in Rn is a solution of this degenerate linear equation. Reason being, if b is 0, then the right hand side of this linear equation is 0, and if you see the left hand side of this equation, 0 times x1, 0 times x2, so whatever is x1 or whatever value we assign to x2 or xn, the left hand side is always 0, because something finite into 0 is 0. So left hand side is 0 and right hand side is already 0 because b is 0. So in that case every vector is a solution of this linear equation, and we say yes, equation has infinitely many solutions. Now the first case was if b is non-zero. In that case the right hand side of this equation is non-zero, but if you see the left hand side, it is 0 times your variable. So you give any value to the variable x1, x2 or xn, left hand side is always 0 and right hand side is non-zero. So 0 can't be equal to a non-zero number, so it is not possible. So we say that system has no solution. If an equation is not degenerate, then we say it is a non-degenerate equation. Next is leading unknown in a given equation. So I'm picking just a random equation with 6 variables. So I'm considering a non-degenerate equation, that is at least one of the coefficient is non-zero. So it is 0 times x1 plus 0 times x2 plus 3 times x2 plus 0 times x4 plus 5 times x5 plus x6 equal to 7. So here if you see the coefficients of x1 and x2, they are 0. x3 is the first unknown whose coefficient is non-zero. So this x3 is called the leading unknown for the above non-degenerate equation. Equivalent systems, that is same systems. Consider the following system of linear equations given by 2.1 to 2.m equations in n variables. So this is a given system. Now I will use these equations and I will get a new equations using these given equations. So for this what I am doing, multiply these equations 2.1 up to 2.m suitably by some real numbers c1, c2, cm, then add up all these sides on the left and similarly on the right hand side. So after doing all these calculations, means multiply all these equations by C1, C2, Cm and then add up, I will get a new equation, that is 2 star, where the coefficient of x1 is C1 A11 plus C2 A21 plus Cm AM1, and similarly we have coefficient of x2 and xn. Then this 2 star is called a linear combination of the equations in the given system 2.1 to 2.m, and any solution of this given system is always a solution of this new equation given by 2 star. For more clarity of equivalent systems, let us consider this example. 2x plus y plus z equal to 5, equation number 3, and then equation number 4, minus x plus 3y minus z equal to minus 5. Then clearly x equal to 2, y equal to 0 and z equal to 3 is the solution of these equations given by 3 and 4. Now consider a linear combination of these equations. I am multiplying equation number 3 by 3 and equation number 4 by 2 and just add these two equations. Then on the left hand side we have 4x plus 9y plus z, this is equal to 11 on the right hand side, and we can see clearly that x equal to 2, y equal to 0 and z equal to 3, this is also a solution of this new equation given by 5. So out of these three equations 3, 4 and 5, we can pick any pair of equations to form three different systems of equation, and all these three systems, they are equivalent and they have the same solution set. For a given system of equations, now we have to find out its solution. So while finding the solution, we do a lot of calculations. We add them, we subtract them, we multiply them by some numbers. So all these operations are called elementary operations. When we apply these operations, we get a new form of equations. So the new system and the starting one, both these systems are always equivalent. So I am defining now elementary operations. Interchange two of the equations. Suppose we have a system of equations defined as R1, R2 and Rn. These are m equations in n variables. So interchange of two equations means out of these m equations you can interchange any of the two equations, ith and jth equation. Then again there is no change in the system. Just interchanging the position of the equations doesn't make any change in the system of equations. So mathematically the interchange of two equations is rewritten as Ri left right arrow Rj, that is interchange ith equation and jth equation. Second elementary operation is we can replace an equation by a non-zero multiple of itself, and replacement of ith equation by a scalar multiple k of itself is represented as Ri goes to k times Ri, that I am multiplying ith row by some scalar k. Third elementary operation is that we can replace an equation by the sum of a multiple of another equation and the equation itself. For example, replacement of jth equation, that is Rj, by the sum of scalar multiple of ith equation Ri and itself is represented as Rj right arrow Rj plus k times Ri. Now this is very important theorem. Suppose a system A of linear equations is obtained from another system B of linear equations by a finite number of elementary operations, then A and B have the same solution set. Now I am explaining all these elementary operations by considering examples. Interchange of two equations. So consider the system A with three equations in three variables. 2x plus y plus z equal to 3, minus 3x minus y plus 2z equal to 7, x plus y plus 3z equal to 9. Now see the operation. R2 and R3, interchange these two equations. I have given different colors. So even if I interchange these two equations, I will get another system B. right? You can see the position of blue equation, that is x plus y plus 3z equal to 9, and the next one is minus 3x minus y plus 2z equal to 9. So these two systems, clearly you can see that these two systems are equivalent, and solving system A is same as solving the system B. Now second elementary operation, that interchange an equation by a non-zero multiple of itself. So consider system A with the two equations, x plus y equal to 1, and second equation is x minus y equal to minus 2. You can solve the system and we say that x equal to minus 1 by 2, that is minus half, and y equal to 3 by 2. This is a unique solution of this system of two equations in two variables. Now consider system B, and how I am getting the system. I am changing first equation to 2 times first equation. So now x plus y, that is red equation, x plus y equal to 1. Now I am rewriting this one as 2x plus 2y equal to 2 in the second system B. Second equation I am just keeping as it is, x minus y equal to minus 2. So now I have a new system B, and we got this by applying second elementary operation. So finally I have 2x plus 2y equal to 2, x minus y equal to minus 2. Now you can solve this system graphically also. Just draw these two lines in a plane. You will get a solution as x equal to minus half, y equal to 3 by 2. And this is again the same as the solution of system A. So I can say that both the systems A and B are equivalent. Now the third elementary operation, that replace an equation by the sum of a multiple of another equation and the equation itself. So I am considering the previous example, system A as x plus y equal to 1 and x minus y equal to minus 2, and as discussed earlier, its unique solution is x equal to minus half, y equal to 3 by 2. Now I am applying this elementary operation, that change second equation to sum of second equation plus 2 times first equation. So I am rewriting another system B. First equation is same, x plus y equal to 1, and see the second equation now. It is 3x minus y equal to minus 3. So if we see system B, it is different. One equation is same, but the second equation is different than the second equation of given system A. Now we can solve this system B, and we see that its solution is unique, and that is given by x equal to minus half, y equal to 3 by 2. So we see that even we apply this elementary operation, the new system is again same and it has the same solution. So again we have system A and system B, and both are equivalent systems. Let's move further, and now we discuss how to find out the solution of given system of equations. I am starting with the basic one equation in one unknown. So consider the linear equation defined by equation number 6, that is ax equal to b. We have only one variable x, a and b are constants. So the solution of this equation depends on what are the values of these constants a and b. So the first option is, if a is non-zero, that is the coefficient of variable x is non-zero, then x equal to b by a is a unique solution of this equation number 6. If coefficient is 0, but right hand side number b is non-zero, then ax equal to b has no solution. Clearly, if a is 0, then on the left hand side we have 0 into x, where x is any real number, it is always 0. But right hand side is b, which is non-zero, and 0 can't be equal to a non-zero number. So in that case we say equation 6 has no solution if a is 0 and b is non-zero. Now the third one, if a is 0 and b is 0, then in that case every real number is a solution of equation number 6, because 0 into any real number is 0 and right hand side b is also 0. So this equation is satisfied for every real number, and we say equation has infinitely many solutions. Take the example 2x equal to 4. then clearly x equal to 2 is a solution. Consider the second one, 0 times x equal to 5. Then clearly in this case x is not defined and we say this equation has no solution. Last one, 0 into x equal to 0. Then clearly you can give any value to x, say 1, 2, 0.5 or any other real number. Then this equation is always satisfied and we say that every real number is a solution of this equation. Let's consider system of two linear equations in two unknowns x and y given by equation number 7 and 8. Equation 7 is a1x plus b1y equal to c1. Equation number 8, a2x plus b2y equal to c2. Before starting its solution, let's recall the equation of a straight line with slope m and y-intercept as c. Then it is given by y equal to mx plus c. I'm discussing this because later on we will see the geometrical interpretation of the solution of these two equations in two unknowns. So if I use this concept of a slope y equal to mx plus c, then using this the slope of line 7 is minus a1 over b1 and slope of line 8 is minus a2 divided by b2. Now given a system of equations, there are three options: unique solution, infinitely many solutions, and no solution. So I'm discussing the first one, that system has a unique solution. So let's discuss this concept geometrically first. So here I'm taking two equations. First one is x minus y equal to minus 1. This one I am representing by a red line. You can see the graph. Slope of this line is 1. Second equation is 3x plus 2y equal to 12 and slope of this line is minus 3 by 2. Clearly these two lines are not parallel, they have different slopes, and if we see the graph, they are intersecting at a unique point and that point is 2, 3. So we say that this system has a unique solution and that solution is 2, 3. And we got this unique solution when the slopes are not equal. So we will use this observation and we find out the mathematical condition for the existence of a unique solution for a system of two equations in two unknowns. So I'm just rewriting these two equations: a1x plus b1y equal to c1, a2x plus b2y equal to c2. So geometrically two linear equations in two unknowns have a unique solution if they are not parallel, that is they have different slopes. So using this one I'm comparing the slopes of these lines. Minus a1 over b1, this is not equal to minus a2 over b2, that is I can say that a1 over a2, this is not equal to b1 over b2. So we have this condition a1 b2 minus b1 a2, this is not equal to 0, and this condition can be represented in the form of determinant a1 a2 b1 b2, this is non-zero for a unique solution. There is no restriction on the right hand side values c1 and c2. Second case, when the given system of two equations in two variables has no solution. So geometrically we have a situation like this. Here I am taking two equations, x plus 3y equal to 3. I am representing as a red line. Slope of this line is minus 1 by 3. And if you see the y-intercept of this line, it is 1. Second equation is 2x plus 6y equal to minus 8. I am representing as a green line. Slope of this line is minus 1 by 3. And the y-intercept of this line is minus 4 by 3. If you see these two lines, these are parallel. They have same slope minus 1 by 3 for the red line as well as for the green line, but they have different y-intercepts. So if we have a situation like this, in that case we say system has no solution because these two lines are not at all intersecting at any point. So these two equations are not satisfied simultaneously, and we have situation where the system has no solution. Now this geometric condition of a non-existence of a solution or no solution, we simplify this equation in terms of mathematical form. So I'm just rewriting those two equations, a1x plus b1y equal to c1, a2x plus b2y equal to c2. So for no solution, lines are parallel but they have different y-intercepts. So let's start with the first one, that two lines are parallel. Then their slopes are equal, so we get minus a1 over b1, this is equal to minus a2 over b2. I'm writing this by equation number 9. I can simplify this, and finally I have a1 over a2, this is equal to b1 over b2 in equation number 9. So if you see equation number 9, here I am saying that the first ratio a1 over a2, this is equal to b1 over b2. That is, the ratio of coefficients of x in these two equations is same as the ratio of the coefficients of y in these two equations. If it is so, then we say that two lines are parallel. So finally I have equation number 9. Second condition is that the two equations have unequal y-intercept, which implies that c1 over b1, which is the y-intercept for the first line, this is not equal to c2 over b2, which is the y-intercept of second line. We can find out this intercept just by putting x equal to 0 in these equations. So this implies that b1 over b2, this is not equal to c1 over c2 given by equation number 10. So from equation number 9 and 10, we have the mathematical condition for the non-existence of a solution, which is a1 over a2, this is equal to b1 over b2, not equal to c1 over c2. Consider a system of two equations in two variables with a situation where we have infinite number of solutions. In this case, geometrically, these two equations are same. For example, the first equation is x plus 2y equal to 4, and second equation is 2x plus 4y equal to 8. So if we divide the second equation by 2, we get exactly the same equation as the first one. So geometrically we can say that we have infinitely many solutions if they have the same slope and they have same y-intercept. I have drawn two different graphs, otherwise these two lines, they are same. So just from the graph we can see that both are exactly same. So in this case, every point on this line is a solution of this system of equations. Now the mathematical condition for the existence of infinitely many solutions is as, consider these two lines a1x plus b1y equal to c1. Second equation, a2x plus b2y equal to c2. There are two conditions. First, these two lines are parallel, that is, they have the same slope and they have same y-intercept. So using the slope condition, we have minus a1 over b1, this is equal to minus a2 over b2, which implies that a1 over a2, this is equal to b1 over b2 given by equation number 11. It is the same as discussed in the previous case. Now the second condition, that they have equal y-intercept, this implies that c1 over b1, this is equal to c2 over b2, which implies that b1 over b2, this is equal to c1 over c2 given by equation number 12. Now we can combine equation number 11 and 12, and finally we have the following condition for the existence of infinitely many solutions for a system of two equations in two variables. a1 over a2, this is equal to b1 over b2, this is equal to c1 over c2. Consider the system of two equations in two variables x and y given as x plus ay equal to 4 and ax plus 9y equal to b, where a and b are unknowns. There are some constants, but we don't know what is the value of a and what is the value of b. So we want to find out all those values of a for which the system has a unique solution, and the pair of values a and b for which the system has more than one solution. Here you can apply the geometrical conditions, or we can just apply the simple elimination method. So first I am trying to eliminate x from these two equations. So for this one, multiply first equation by a and then subtract these two equations. We have a square minus 9 into y. This is equal to 4a minus b. Now this is system of one equation in one variable, and it is of the form ax equal to b. And as discussed earlier, this system has a unique solution provided the coefficient of x is non-zero. So we have a square minus 9. This is non-zero. So this implies that a is not equal to plus minus 3. Other technique is that we can use the geometrical concept here, that this system has a unique solution if these two lines are not parallel, which implies that minus a1 over b1, this is not equal to minus a2 over b2, that is slope of these two lines, which implies that 1 by a is not equal to a by 9, that is the slope of the second line. So finally we simplify this, we get the same value, that a is not equal to plus minus 3. Now the second case, system has infinitely many solutions, and geometrically we have infinitely many solutions if these two lines are parallel and they have the same y-intercept, and it can be written in the form of a1 over a2, this is equal to b1 over b2, this is equal to c1 over c2. So we can just find out these ratios from the equations, and finally we have 1 by a, this is equal to a by 9, this is equal to 4 by b. Now these are two equations, which implies that a square equal to 9 and ab equal to 36. When we simplify this, we get a is equal to plus minus 3 and ab product is 36. So using this, we have two combinations, 3 and 12 and minus 3 and minus 12. So if these are the values of a and b, in this case the system has infinitely many solutions. Next, I am discussing about the system of three equations in three variables. What are the different situations where we have a unique solution, infinitely many solutions, or no solutions? So consider the system given by x plus y plus z equal to 1. Second equation is x minus y plus z equal to 3, and the third one is 2x minus y plus z equal to 5. I'm using software here and I can draw these three equations. These are planes. You can see here three different planes. Now this system has a unique solution. So let's see what exactly is going on in this system geometrically. This is a different geometrical view of the same system, and you can see here this yellow star. This is the point of intersection of these three planes. You can see these three lines. It's some sort of pyramid type of shape. So these are these intersection of these planes pairwise, and this point star is marked where all these three planes are intersecting. So this is the common point, and we just have one point of intersection for all these three planes. So this system has a unique solution. Second situation, when the system of three equations in three variables has no solution. So for this one, I am taking these equations: x plus y plus z equal to 1, x minus y plus z equal to 3, 3x minus y plus 3z equal to 15. So again, I'm using the software, and finally I have this graph, three different shades for each of these planes. You can compare these shades corresponding to green equation. We have a plane, and this one is 3x minus y plus 3z equal to 7. Then for dark blue and light blue colors, we have the corresponding planes. This is the geometrical view of the same system of equations as discussed on the previous slide. And in this graph, we can see easily that these three planes are intersecting, but they are intersecting pairwise. There are three lines of intersection for these planes, but there is no common point where all these three planes are intersecting with each other. So we say the system has no solution. Consider this example, 3 equations in 3 variables, and this system has no solution. In this one, we can see from the graph that 2 planes are parallel and the third plane is intersecting these 2 planes. There is no common point of intersection for all these 3 planes. So we say system has no solution. Now consider this system, 3 equations, 3 unknowns, and it has no solution. In this situation, all the 3 planes represented by these 3 equations, they are parallel. So there is no common point of intersection for these 3 planes, and again we say that system has no solution. So we can say that there are different possibilities for a system of 3 equations in the case of no solution. Consider the system of 3 equations in 3 unknowns with the condition that system has infinitely many solutions. So I am taking here x plus y plus z equal to 1, x minus y plus z equal to 3, and the last 3x minus y plus 3z equal to 7. From the graph we can see that all these 3 planes, they are intersecting in a line. So every point on this line is a solution of the system of equations. Just a small observation in this case, that the third equation can be obtained from equation number 1 and 2. We multiply equation number 2 by 2 and then add in the first equation. We will get the third equation. So basically, we can reduce this system in just system of 2 equations in 3 variables.